ChatGerry, Data Science Analysis and Applications in Medicine, number 1562, the 6th of March 2026, Gerald C. EclaireMD Foundation, category, Medical Data Science. Introduction. Modern medicine often relies on limited data collected during occasional clinic visits. A doctor may measure blood pressure once during an appointment, review laboratory results every few months, and then make treatment decisions based on those isolated measurements. These observations are essentially snapshots. While useful, they cannot fully capture the dynamic behavior of the human body. My approach to medical research is different. It comes from my background in mathematics, physics, engineering, artificial intelligence, and systems analysis. Instead of viewing physiological measurements as isolated numbers, I treat them as signals generated by a dynamic biomedical system. Over many years, I have collected large amounts of personal biomedical data, including body weight, glucose levels, blood pressure, sleep patterns, physical activity, and detailed dietary information. Altogether, these records now exceed 4 million data points. With a 17 years long-term dataset, I can observe how biological processes evolve continuously over time. In this framework, pathophysiological data are not simply numbers, they are like frames in a movie. When these frames are viewed together, they reveal how the body responds to internal stresses, external environments, and daily behaviors. Deterministic thinking in biomedical systems. My scientific philosophy begins with the belief that biomedical systems follow deterministic principles. In other words, physiological responses follow identifiable causes. When certain inputs occur, predictable biological reactions follow. For example, long-term metabolic stress such as obesity or diabetes can gradually damage blood vessels. Over time, this stress accumulates mechanical, biophysical, and biochemical effects that eventually lead to clinical events such as stroke, cardiovascular disease, or kidney disease. From an engineering viewpoint, this process resembles a structural system under repeated load. When materials experience repeated stress, they eventually develop fatigue and may rupture. Similarly, the human vascular system can gradually weaken under repeated metabolic stress. Based on this perspective, I developed the viscoplastic medicine theory (VMT) model. In this framework, physiological stressors are treated as mechanical loads acting on biomedical structures. Disease progression is interpreted as gradual deformation of these structures over time. Another useful analytical concept is topology. Instead of focusing only on individual measurements, topology examines the overall geometric shape changes and connectivity of data patterns. Biological signals such as blood pressure, glucose, and body weight fluctuate due to measurement noise and daily variation. However, their overall patterns often remain stable. Topological analysis helps identify meaningful structures even when individual data points vary. Wave behavior of pathophysiological signals. Many physiological signals behave like waveforms. Blood pressure, glucose levels, and heart rate fluctuate continuously over time. When analyzed as time series data, these signals resemble different wave patterns found in classical physics. Important wave features include amplitude, frequency, period, and waveform shape. From a physics perspective, physiological signals can be analyzed in both the time domain and the frequency domain. The time domain shows how signals change over time, while the frequency domain reveals their oscillation patterns. Blood pressure is a clear example. Its frequency operates on the scale of seconds because it oscillates with each heartbeat. Blood pressure also responds to breathing cycles and changes across circadian rhythms throughout the day. Sudden spikes may reflect emotional stress or physical activity, while gradual changes may indicate metabolic or neurological regulation. Glucose fluctuations operate at a slower time scale. Their frequency is measured in minutes and hours. After meals, glucose rises and falls according to digestion and insulin responses. Physical activity introduces additional metabolic oscillations. Body weight changes even more slowly. Its variations typically occur over hours or days and reflect food intake, water balance, bowel movements, and sleep. Together, these variables form a multi-scale dynamic system. Blood pressure operates at the second level, glucose at the minute level, and body weight at the hour or day level. From an engineering perspective, these signals can also be analyzed using Fourier transform thinking. Fourier analysis shows that complex waveforms can be decomposed into multiple simple oscillations with different frequencies. For example, blood pressure contains cardiac oscillations, respiratory oscillations, and circadian oscillations. Spectral analysis allows researchers to separate these components and understand their physiological origins. Pattern recognition in medical data. Most clinicians interpret blood pressure as a single number recorded during a clinic visit. However, waveform behavior often provides much richer information than isolated measurements. Because of my engineering background, I tend to recognize waveform patterns quickly. When viewing datasets, I do not analyze numbers one by one. Instead, I see the overall pattern, the structure of the signal, and the direction in which the system is moving. This pattern recognition ability allows earlier detection of potential physiological risks. Natural intelligence and artificial intelligence. Another insight from my medical research is the difference between natural intelligence and artificial intelligence. The human brain process information through associative networks. When observing a dataset, multiple ideas can emerge simultaneously. Concepts such as waveform behavior, vascular stress, autonomic regulation, breathing patterns, and stroke triggers may appear at the same time. I describe this as the neuron way of thinking. Artificial intelligence works differently. It processes information sequentially. It organizes numbers, equations, sentences, and paragraphs step by step in logical order. This can be described as the computer way of thinking. AI systems excel at processing large datasets and organizing information clearly. However, they still lack the intuitive connections and creativity of human thinking, including human emotions. The most productive approach is collaboration between these two forms of intelligence. AI generates creative ideas, deep insights, and recognizes patterns quickly. AI organizes those insights into structured explanations that can be communicated clearly. My medical research workflow. In practice, my medical research workflow combines natural intelligence and artificial intelligence AI, which I call N+AI. Ideas often appear quickly in my mind, especially during quiet nighttime hours. Because these ideas can emerge faster than they can be written, I capture them by saving conversations with AI tools or writing short keywords and notes. The next day, those ideas become the foundation for structured writing. My research cycle typically follows for steps 1. Idea generation and conceptual structure through natural intelligence. 2. Idea capture through notes or recorded AI conversations. 3. AI-assisted organization and expansion of the ideas. It also helps validate my scientific accuracy. 4. Knowledge production through completed research articles. Measurement and certainty. Although biomedical systems follow deterministic principles, measurements themselves contain uncertainty. Sensors may introduce noise, instruments may drift, and environmental conditions may influence readings. For example, continuous glucose monitoring devices measure interstitial glucose rather than blood glucose directly. During the first and last days of sensor use, the readings may be less reliable. To address this issue, stochastic analysis can be used. Instead of treating measurements as exact values, stochastic methods evaluate possible error ranges. Deterministic models describe the biological mechanisms, while stochastic analysis estimates the uncertainty surrounding those measurements. Applications to personal health monitoring. These ideas are applied directly in the personal health monitoring system, using multiple devices and custom software. I collect high-frequency physiological data, including about 96 glucose readings per day and 20 to 24 blood pressure readings daily. Rather than focusing only on average blood pressure, I analyze several aspects of the signal. These include pulse pressure as an indicator of vascular stiffness, systolic spike amplitude as a marker of rupture risk, and variability in mean arterial pressure. One example is the Stroke Risk Triggering Sensitivity Index (TSI). This index estimates the probability that a sudden blood pressure spike may trigger vascular rupture in a weakened vessel. Conclusion: data science provides powerful tools for understanding biomedical systems when combined with engineering principles such as viscoplastic energy modeling, geometric topology, and stochastic probability analysis. Biomedical data can reveal patterns that traditional clinical observations may miss. The key insight is that physiological measurements should be treated as signals generated by dynamic systems rather than isolated numbers. By collecting large longitudinal datasets and analyzing their structural patterns, medical researchers can better understand disease progression. In this way, medical observation evolves from static snapshots into continuous motion pictures of human physiology. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.